All right, let's look at number 9 on exam 2 from 2014. It has the chair conformation. So we have a chair like this, guys. And we have a bulky base. The question says, show the ring flip and the product of the reaction below. So you should look at this, and first question you always ask yourself is what? What type of alkyl halide do you have? You have a secondary alkyl halide. So you automatically should be able to eliminate two possibilities. So you know it can't be SN1 or E1. So then you ask yourself, then you know it's either E2 or SN2. And then you say what kind of, so hopefully you have a reactive nucleophile base, and I think we have a reactive nucleophile base with a negative charge. Then we see how big it is. This is a pretty big one, right? T-butoxide is a big one, so we should be thinking E2. Once we got to E2, then we know E2, the actual conformation it has to be in is antiperiplanar. So in these rings, when you're a cyclohexane ring, that means you need to be axial. Right? The leaving group needs to be axial. So right now, this bromine is equatorial, so it needs to be axial. So we need to do a ring flip. Now the bromine's pointing up. It's always going to be pointing up. What we're going to change here is whether or not it's axial or equatorial. So if it was equatorial and we do a ring flip, it becomes axial, but it stays up. Right? And vice versa. If you look at this ether piece here, this is pointing up, but it's axial. When we do the ring flip, it's still going to be up, but it's going to be equatorial. The other thing we should do here is number our carbons. 1, 2, 3, 4, 5, 6. That's a bad 5. Helps us see what's going on. So in a ring flip, right, if this is the head of the chair and this is the feet, the head goes down, the feet come up, right? So let's see. Draw it the other way. So 4 is now here, and 1 is now here, right? 4 comes down, 1 comes up. 5, 6, 2, 3. So on 1 was the bromine, and it was up and equatorial, so now it has to be up and axial. Good. Carbon 2. Oh, go ahead.
Okay, so I get how you get the 4 and the 1, but then I don't understand how you get 5 and 6 on the bottom part of it and 3 and 2 on the top, because I thought the opposite.
So think, as you see this come down, 3 is going to shift over here, and 2 is going to go down, right? So the easiest way to do it, I mean, I just pull these and I just go 4, and I just know 3 and 2 are following in line. Okay. Right. It can be hard to see those other ones shifting, but you should be able to see 4 and 1. Yeah. And then that's why the numbering is really important to help see it. Right, so here the bromine's axial and it's up. Carbon 2 had a methyl and it was down, and it was equatorial. That means it's going to be down and axial now. You can draw that all the way down there. Carbon 6 had a O-methoxy, and that was axial and up, so now it should be equatorial and up, hopefully. Now we got to look at this and say, well, bromine is axial, good, but the actual hydrogen also needs to be axial too. So where's the hydrogen that's axial? What beta hydrogen is axial? Which carbon number? 6, right? So it should be 6, because notice, kind of hard to see here, this carbon 2, as it goes behind there, that methyl is axial. There is a hydrogen on carbon 2, but it's equatorial, so it's not going to be antiperiplanar. So, in this case, and you could have drawn it other ways. That goes there, right? Because you can see this antiperiplanar relationship between the H and the leaving group. And so the new pi bonds between which two carbons? 6 and 1. And two.
Okay, then draw that in a ring.
And then you could draw, if you wanted to, you could also draw it like this. If I'd renumber these carbons, 1, 2, 4, 5, 6, 1, 6, 5, 3, and 2. So these are equal. Yep.
Wouldn't
Oh, I forgot something. Sorry. Hold on a second. There you go.
Wouldn't having the alkene and the cyclohexane make that completely straight and flat?
Nope. What's the bond angle for an sp2 hybridized carbon? What's the bond angle right here?
120.
120. It's okay. It'll be strained, but not to the point where it can't form.
So
It's not. Yeah, it can handle the strain. Yes, you can form. Yep, you can form alkenes in 5 and 6 member rings for sure. Yep, you can handle it. Okay.
If I numbered my chair different, but I still got the same result.
Same. So okay. Yep, totally okay. Yeah, I just remember. I'm taking these numbers as arbitrary. I'm not doing like some sort of naming thing. I'm just being consistent. So I just, however you want to do it, it's fine. All right, taking a look at number 2 from 2014 exam 2. This one says rank the nucleophiles below from strongest to weakest in DMF. So DMF is our solvent, right? So that is, and you don't necessarily need to know this. You should know what kind of solvent it is. What kind of solvent is this?
Aprotic.
Polar aprotic. Right, so polar aprotic. So our nucleophiles we have here are F minus, I minus. So it says rank the nucleophiles in DMF. So DMF is a polar aprotic solvent. Right? So no hydrogen bonding. No bonds to heteroatoms. So the easiest thing to do, I think, in these problems is to box it in. So which one's the most reactive, which one's the least reactive? Right? So which ones are going to be the most reactive right off the bat you should be able to look at for nucleophiles? The ones that are charged, F minus and I minus, right? You should certainly recognize these as being the best nucleophiles. They have negative charges. But the question is, which one's going to be the better nucleophile in the polar aprotic solvent? So an aprotic solvent, does that do anything to the nucleophile? Does it hinder the nucleophile in any way, shape, or form? No. So if you don't hinder the nucleophile, which one is the most reactive? F minus is. Why is F minus the most reactive? It's smaller, so it's just going to be the most reactive, right? So this would be ranked number 1 in a polar aprotic solvent. Now, if we and then that means I minus would be number 2. Now, if we were a different type of solvent, if we were in methanol, right, a polar protic solvent, it'd be the other way around. Then I minus would be the better nucleophile, right? Because then it's about how big you are and how hard it is to surround. If the solvent can interact with the nucleophile, right, the bigger the nucleophile, the harder it is for that solvent to completely surround it. So in an aprotic solvent, F minus is better. But in a protic solvent, where the solvent can interact with the nucleophile, I minus would be the better nucleophile. Does that make sense? So now what do we have left? Now we have, let's say we have nitrogen and oxygen things. Anybody have an opinion on this one? What do we want to do next? The oxygen one's going to be what? What do you guys? Well, so we're comparing oxygen and nitrogen. What do we know about oxygen and nitrogen? If you look at the periodic table, which one's more likely to give up their lone pairs, oxygen or nitrogen? So which one's going to be a better nucleophile? So which one should be ranked last? Which one should be ranked last? The carboxylic acid should, right? If oxygen, right, has lone pairs and is more electronegative than nitrogen, it should be the least likely to give up lone pairs, least likely to react. Right? Nitrogen, nitrogen, oxygen. Yep.
Under key of it as fourth, you have.
Yeah.
That's what Mike says.
Yeah, it's confusing.
I think I know why I did that. I think.
Those poor kids.
Whether I want I think I made the key this year. Whether I want you guys to. So there's a double factor here. I would accept either or. I would accept this as 4 or 5. I would accept this as 4 or 5. And but here's a better question. Can someone tell me why?
2 hydrogen first one.
Nope. Keep thinking close. What about resonance?
So for the acid, the double bond to the oxygen is pulling the electrons more. Wait, let me explain the nitrogen. So for that one, the oxygen is super electronegative, so it's pulling.
Which one's more likely to do resonance? Which one's more likely to do resonance, nitrogen or oxygen? Who's more likely to share electrons? Who's more likely to do resonance? So that's right. So the problem is that this will also do a lot of resonance. And if it's doing resonance, that doesn't make the nitrogen very nucleophilic, does it? So there's 2 factors involved here that's why I would take both answers. Right? Because for the same reason you're saying that nitrogen is more reactive than oxygen, it's also the same reason why nitrogen does the resonance structure more. Right, see that? Mm-hmm. So it's really, what factor do you mean? They're both last. I wouldn't put this question on there again. We all can agree this is 3 though, right? You can agree that resonance will make you less nucleophilic, right? Because you're spreading the charge out. So the idea here is if you have resonance, you're less nucleophilic, so you spread the charge out more. Yeah?
So if you put it into a polar product, is that going to completely flip the whole order?
Nope. All it's going to flip is the charge things. The polar product only affects things with size.
Okay.
Right? So as we go down the periodic table, so the polar product part only affects as we do with the size. Right? The bigger you are, the more reactive you are in a polar product solving because you're not being surrounded as much.
So then 3,
4, and 5 have nothing will not be changed with the solvent.
Cool.
Yep, will not change with the solvent. So the non-Zaitsev rules. So there's 3 ways to get non-Zaitsev products of the less substituted alkene. The first one is the easiest one to remember, hopefully. It's conjugation. If you have a choice between being conjugated or having a more substituted alkene, you'll always pick conjugation. So if I showed you 2 alkenes, which alkene do you think is more stable? A or B? A is. So you're going to try to, if you have a choice, right, let's say that these could have came from this starting material, right? And then you label your beta hydrogens, right? Beta hydrogens. We take the beta hydrogens from which carbon instead? I always want to take it from 1 because conjugation is more important than substitution of the double bond. So conjugation is more important, more stabilizing. A is more stable than B. So that'd be the first one. The second one, you need a bulky base and a bulky alkyl X. By bulky, I basically mean tertiary. It has to be a tertiary. Alright? So let's see. So let's say we have something like this. You have a tertiary alkyl halide, and we treat it with a bulky base. We draw on the beta hydrogens. How many types of beta hydrogens are there in this molecule? 2 types. And so even though, if I number these 1, 2, 3, 4, 5, what beta hydrogens are we going to take? Or which ones are we not going to take? 4, right? Just because tertiary alkyl halide, bulky alkyl, bulky base, bulky alkyl halide, it's going to be hard to get to these. So we're actually going to attack either 1 or 3. So we can attack 3, sure.
Doesn't matter.
Doesn't matter. They're the same, right? If we did a proton NMR, there'd be the same peaks there. So there'd be our final product. Alkene either between 2 or 3 or 1 and 3. Yeah.
We can do this after we go through the exceptions, but on the second one for number 6.
Okay, and the final non-Zaitsev way is with fluorine as a leaving group. So that's kind of a completely different mechanism, essentially. So let's say you have fluorine like this, strong bulky base. Draw on the beta hydrogens. Whoops. Number our carbons, 1, 2, 3, 4. Where should we take the H from? 2 or 4? We're going to take it from 4. And the reason why we do that is because we make an actual carbanion intermediate here. So we make this carbanion. And if we're going to make a carbanion, because fluorine's such a bad leaving group, it essentially won't leave at once. It'd rather have you make a carbanion first. And carbanion rules are just the opposite of carbocation rules. So carbocations are stabilized by hyperconjugation, which is right pushing electrons towards an empty p orbital. Carbanions are just the opposite. They hate hyperconjugation. They're electron rich. They don't want electrons pushed towards them, so they want to be less substituted. So it forms that. Then finally, eventually, the fluorine will leave. You get the alkene on the less substituted carbon. Okay, let's look at a reaction with a benzylic position. Let's give 2 examples. Let's look at these 2. See if you guys can tell me the possible products for these. So for the first one, what do we do? What do we got here? What kind of alkyl halide do we have? Primary benzylic, right? So that could be anything, right? That doesn't narrow down SN1, SN2, E1, E2, nothing at all. We look at the nucleophile then. What kind of nucleophile do we have? Reactive or less reactive? Reactive, so that narrows it down to SN2 and E2. When we look at the size of the nucleophile, how about the size of the nucleophile? Is it very big? It's small. But it's also, are there any beta hydrogens?
No.
There are no beta hydrogens. Could you ever do an E2? No. Not if you wanted to. So it is SN2 here. Do we need to worry about stereochemistry here?
No, it's not John Richard.
Nope, because there's no. That's actually not an asymmetric center there anyway, so don't even worry about it. 2 H's there. All right, what about the last one or the second one? What kind of alkyl halide do we have? Secondary benzylic. That's right. So that narrows it down to nothing. So what kind of nucleophile do we have? Reactive or not reactive?
Reactive.
So SN2 or E2? Which one are we thinking here?
E2.
I would say this is going to be E2 and SN2. The nucleophile here is, it's small. Nucleophile is small. Why did you pick E2?
It's more
Conjugation, right? That'd be a great reason to pick E2.
But the SN2 is still happening.
SN2 would probably be the minor product here.
So if we did the one you
Depends on how I format the question, right? If I ask you what a major product is, conjugation usually is pretty important. But if you wrote this is a really small nucleophile, I think it's going to do SN2. But I think conjugation is a better answer. I think E2 would be the major product here.
Wouldn't it take a lot of energy to break the benzene ring for conjugation?
Let's be careful here. Let's look at the mechanism though. So there's the beta hydrogen. The E2 product is going to look like right. So it is conjugate now. So it's not like we're breaking conjugate. We're adding more pi bonds to the system. That's right. So I would say this would be the major. The E2 would probably be the major. And the SN2 would probably be the minor. But it'd still be there, for sure. Maybe you'd made methanol. Talk about epoxides. So epoxides are a little different because they actually have two different ways to make these. Right? Normally the starting material is only one thing, right? An alkene or an alkyne or something like that. But epoxides can actually come from two different places. So let's just take a generic epoxide here. And where did it come from? So this epoxide, if you look at it, it has the methyl is coming at you and the H is going away from you. So that could have came from, if we go retrosynthetic backwards, it could have came from, first number of carbons, 1, 2, 3, 4. What could have it came from? Epoxide. What could it come from? The one you learned about first. Nope, that was the second one you learned. Chapter 6 stuff. What was the starting material? An alkene. And now in this case, what kind of alkene? Because be careful, look at this. There's some stereochemistry here.
The same side.
This is the same side alkene, that's right. What's on the same side? 1 and 4 are. Do you guys know how to make cis alkenes? Where do cis alkenes come from?
No.
You should know. Alkynes? I can just keep going back. Right? So we could have made this, and we could have made this with MCPBA. But notice, right, the methyls are on the same side. The epoxide is just like the Br2, right, the bromonium ion that adds from one side. So that's one way to make an epoxide from an alkene. Notice how it has to be cis. The other way, right, was what? You had to make it from a Br and the OH, right? If we go back one step, it would have had to have come from, in this case, the OH on one side, the Br on the other, and the H here. You see how the Br and the OH are trans to each other? So if I take this back one step, what kind of alkene did this come from?
Br minus alkene.
Alkene.
Wait.
I gave it away. It comes from an alkene, right? I think I just said it as it was. Right? It would have to come from the same type of alkene. Right? Because the methyls had been, again, 1 and 4 here are on the same side. It's the same side. It is always true.
That's a big home run one. I want to get a tattoo for him.
So if we had to react this to get the OH and the Br, we'd need what reagents? Br2 in water, right? And then to do the final SN2 here, what reagent do we need? NaH, right? That's sodium hydride that deprotonates the H here, and they can do the SN2. But notice the stereochemistry, right? That's important here. That matters. These stereochemistry implications matter. All right, where the methyl is at. Yeah, Steve.
Just on the next one, could you use NH3 in it somehow?
Yep. NaNH3 or Na, like to make a trans alkene? Or the NaNH2?
Not the NaNH2.
You want to make the trans alkene. So right, I could have done this exact same problem, right? If I would have done this exact same problem, and the only thing I would have changed, I'm making epoxide again, but instead here, I put the H is trans and the methyl's trans. And now, if I take one step back, what kind of alkene must they have came from? If I number 1, 2, 3, 4. Now what kind of alkene? E or Z alkene? E, because now the methyls are trans. Right, if I keep pulling everything back out of the way now. And how would I have made a trans alkene? I could have said one more step back from this would actually be a alkyne. Right? We know how to make alkynes. Or do alkyne? How do we make an alkyne? Where does that come from? How many pi bonds do alkynes have? 2. So how many leaving groups would they need to have to make 2? So if I renumber my carbons here, I kind of slow down here. 4. 1, 2, 3, 4. So what do I need to have here on this thing now?
2 leaving groups.
So where do you want me to put them?
2 and 3.
2 and 3, and I'll put. What do you want them to be?
BR.
BR. 1, 2, 3, 4. Okay. Now let's go forward. If I want to add 2 bromines, or I want to lose 2 bromines here. If I want to eliminate 2 bromines, what do I need to do? NH2. And I need to say how much though? I need at least 2 equivalents, right? Or excess is fine.
So there's not a problem with having more than 2 equivalents?
No, yeah. I know you need, you need to show me that you need more than 1. What if I want to make I have an alkyne and I'll make it a trans alkene? What reagents are those? Make it right? If I going from an alkyne to a trans alkene, what reagents are those? Not H2 Lindlar's, that makes a cis one. Which one's this one?
Palladium on carbon?
Nope, that would reduce it all the way to the alkane. Nope, HBr would make it into a alkene with a BR.
That's the NH.
Nope, BH3 would make it into a ketone. It's the weird one. The Na, remember Na dot in the NH3? Remember that's the sodium, remember the sea of electrons? The sodium or lithium? The sodium or the lithium one? Yeah, we knew the mechanism for that one at some point and everything.
Could we keep it simple and just go with Li.NH3?
That's fine.
Okay.
Yep. I think when I do it that's when we originally taught it, we did Li dot. Just because I know people get this confused with NaNH2.
Yeah.
And the product of actually the trans alkene is NaNH2, which makes it even more confusing. So maybe if I do Na dot always, that'd be the other way to differentiate them. It's Na dot. You're pumping in electrons. Right? We're pumping electrons in to get rid of this pi bond. And then to do the epoxidation, MCPBA. So here's an example, right? It'd be similar if we did the BR-OH thing, but the biggest difference here is if I see these methyls are trans to each other, I had to start with a trans alkene. If I see they're cis to each other, I had to start with a cis alkene or or Z alkene. Right? That's the kind of the take-home message there. So if I was going to make a list, if I was going to make a list of how to analyze a question, right? The first thing I always ask myself is, what type of alkyl X? That's the first question always. That question can really differentiate fast some of these things, right? If it's not tertiary, or if it's not allylic and benzylic, right? You can't make a carbocation, so it automatically eliminates SN1 and E1. If it's tertiary, it also immediately eliminates SN2, right? So that's probably the first question I would ask. The second question I would ask, right, if that doesn't completely help you, right, is how reactive is the nuke/base, right? Because we don't know if it's a nucleophile or base yet, but asking how reactive it is, right? If something has a negative charge, that makes me think E2 or SN2. If it doesn't have a negative charge, that makes me think SN1 or E1. Right? Third thing I'd ask myself, I'm still sitting there, is how bulky is the nuke/base. Right? If it's bulkier, that makes me think more about elimination. Right? If it's smaller, it makes me think more substitution. Right? And maybe the fourth thing I'd ask myself, I would look at possible products. Right? If you're still stuck, you're like, I don't know if it's an elimination or substitution, right? I don't know if it's E1 or... You should at least got it eliminated down between the 1s and the 2s, right? Either know it's E1 or SN1 or E2 or SN2. You should at least got it differentiated there. And you still don't know, I would look at the possible products, right? So like that question we just had before, right, where you guys said E2 makes more sense because this is going to give us a conjugated product versus the SN2, which wouldn't give us a conjugated product. So if it's going to give you a really stable product, then that makes more sense, right? More stable, better. More stable, more likely. All right, so if you can get conjugation, that makes elimination seem a lot better, right, in those cases. So I would say those are the four things. If you can get through those, you can pretty much you can kind of figure it out from there, I think.